Hello everyone and welcome back. In our last video, we explored the powerful Cayley-Hamilton theorem, which states that every square matrix satisfies its characteristic equation. Today, we are going to see how this theorem can make seemingly difficult problems much easier. Get ready to unlock some cool applications. Imagine you were asked to calculate a to the power of 2024 for this matrix A, which is 3113. Calculating A multiplied by itself 2024 times would be incredibly tedious. But fear not, the Cayley-Hamilton theorem provides a much more elegant solution. Let's see how the Cayley-Hamilton theorem can help us find high powers of a matrix. Let us first find the characteristic polynomial of A. And by theory, the characteristic polynomial of A is given by C of lambda is equal to determinant of A minus lambda I. Since A is a 2 by 2 matrix, we could actually use the shortcut method to find the characteristic polynomial of A, and that would be given by C of lambda is equal to lambda square minus trace of A times lambda plus determinant of A. So that would be lambda square minus, in this case the trace is 3 plus 3, which will be 6 lambda plus the determinant of this matrix is A. So thus we have the characteristic polynomial of A is C of lambda equal to lambda square minus 6 lambda plus 8. Now let us apply the Cayley-Hamilton theorem. As per the statement, A satisfies its own characteristic equation. It means that C of A will be 0, where 0 is the 0 matrix of order 2, that is A square minus 6A plus 8I is equal to 0. Our goal is to find A to the power 2024. So think of dividing lambda raised to 2024 by the characteristic polynomial C of lambda. Applying division algorithm to this, we get lambda raised to 2024 is equal to some quotient polynomial in lambda times characteristic polynomial of lambda plus some remainder in lambda. Now since the characteristic polynomial is of degree 2, the remainder polynomial will be linear, so we will have q of lambda times c of lambda plus a lambda plus b, where a and b are real numbers we wish to find. Now next we are going to replace lambda by a, which gives us a to the power 2024 is equal to q of a times c of a plus a times of a plus b times of I. Now we already have that C of A is equal to 0 by the Cayley-Hamilton theorem, and that we are going to replace over here. So we get that A raised to 2024 is equal to A times A plus B times of I. Now we need to find the constants A and B. We can use the eigenvalues of A to help us. To find the eigenvalues of A, we need to solve the characteristic equation, which is lambda square minus 6 lambda plus 8 is equal to 0, and by factorization we get that this is lambda minus 4 times lambda minus 2 is equal to 0, which gives us lambda 1 is equal to 4 and lambda 2 is equal to 2. Thus we have that 4 and 2 are the eigenvalues of the given matrix A. Next, we are going to substitute the eigenvalues of A in the remainder equation, which is lambda raised to 2024 is equal to q lambda times c lambda plus a lambda plus b. Substituting lambda 1 equal to 4, we get 4 raised to 2024 is equal to, the moment you substitute lambda equal to 4, since this is the characteristic polynomial, this will become 0, and so eventually this entire term becomes 0. So we will be only left with the expression a lambda plus b, which is the remainder. Thus we have 4 raised to 2024 is equal to a times 4, that is 4a plus b. And similarly, if I substitute lambda 2 equal to 2 in the same equation, we get 2 raised to 2024 is equal to 2 times of a plus b. Now we have simple linear equations, and we got to solve that to find out the values of a and b. If we perform 1 minus 2, we could get rid of the b and we get that 2a is equal to 4 raised to 2024 minus 2 raised to 2024, which gives us A is equal to 4 raised to 2024 minus 2 raised to 2024 over 2. Now substituting A back in, let's say, equation number 2, we are going to get 2 raised to 2024 is equal to 2 times of A. So that is 4 raised to 2024 minus 2 raised to 2024 over 2 followed by a plus B. And it is easy to see that we can get rid of the factor 2. So thus we have that 2 raised to 2024 is equal to 4 raised to 2024 minus 2 raised to 2024 plus B. So we get B is equal to 2 into 2 raised to 2024 minus 4 raised to 2024. Once we have the values of A and B, we will be substituting it in this equation to get the matrix A. So we have the final matrix A raised to 2024 equal to AA plus BI, and this is going to be A times 3, 1, 1, 3 plus B times 1, 0, 0, 1, which gives us 3A plus B, A, and again 3A plus B. Now next we substitute the values of A and B that we have obtained to get the resultant. So our matrix A raised to 2024 is going to be 3 times of A, that is 3 by 2 times of 4 raised to 2024 minus 2 raised to 2024 plus B, which is 2 times of 2 raised to 2024 minus 4 raised to 2024. Then A, that will be 4 raised to 2024 minus 2 raised to 2024 over 2 A, so that is 4 raised to 2024 minus 2 raised to 2024 over 2, and over here again we have 3A plus B, which is 3 by 2, 4 raised to 2024 minus 2 raised to 2024 plus 2 times of 2 raised to 2024 minus 4 raised to 2024. Let us simplify these values. So therefore A raised to 2024 is equal to, so we have 3 by 2 times 4 raised to 2024 minus 1 times 4 raised to 2024. So that is going to give us half 4 raised to 2024. And then again we have 3 by 2 times of 2 raised to 2024 plus 2 times of 2 raised to 2024. And that is going to give us minus half times of 2 raised to 2024. Over here we have 4 raised to 2024 minus 2 raised to 2024 over 2, and this also is the same, 4 raised to 2024 minus 2 raised to 2024 over 2, and the A22 entry is again half 4 raised to 2024 minus half 2 raised to 2024. Thus, it can be seen that all 4 entries are same, so we can take that common. So we will have half 4 raised to 2024 minus 2 raised to 2024. This is the scalar, and multiplied by 1, 1, 1, and 1. This is the required result which we are looking out for, A raised to 2024. As you can see, even though the power is large, using the Cayley-Hamilton theorem reduces the problem to solving a system of 2 equations and then performing a simple matrix addition and a scalar multiplication instead of multiplying A by itself 2024 times. Let us move to the next application of the Cayley-Hamilton theorem, which is finding the inverse of A. Let us use the same matrix A. We have already found the characteristic equation of this matrix, which was C of lambda is equal to lambda square minus 6 lambda plus 8. And by the Cayley-Hamilton theorem, we have A square minus 6A plus 8I is equal to the 0 matrix. we will rearrange this equation to isolate the identity matrix, and we get that 8i is equal to 6a minus a square, which is equal to a times of 6i minus a. Now let us pre-multiply by a inverse on both the sides. So on the left we will have a inverse times 8i is equal to a inverse times a into 6i minus a. So over here, since I is the identity matrix, this is 8a inverse is equal to, since matrix multiplication is associative, we could multiply these two matrices, which will give us I, and we will be left out with 6i minus a. So it is so easy to see that A inverse is equal to 1 over 8 times of 6i minus a. Now last step which is left is to substitute this matrices. So we have 1 over 8. 6 times I will be the matrix 6, 0, 0, 6 minus A, which is 3, 1, 1, 3, which gives us 1 over 8 times of 3 minus 1 minus 1, 3. Then there you have it. We have found the inverse of A using the Cayley-Hamilton theorem, which is often simpler than using methods like finding the adjoint and dividing by the determinant. As we have seen today, the Cayley-Hamilton theorem is not just a theoretical result, it has practical applications in simplifying matrix calculations. Finding high powers of a matrix and calculating the inverse become much more manageable with this powerful theorem. It's a testament to the beauty and utility of linear algebra. If you found this video helpful, please give it a thumbs up and subscribe for more linear algebra tutorials. Let me know in the comments if you have any questions or suggestions for future videos. Thanks for watching and happy learning.